Hello everyone, I'm Naoki Akai. In this talk, I'm going to focus on how we can detect localization failures. I know in this workshop, we are focusing on how we can assess quality of the map. I think this motivation is coming from, so we would like to realize safe autonomous navigation because the map has a very important role in the autonomous navigation. And my research motivation is also coming from this motivation because localization also has a very important role in the autonomous navigation. And to listen, I'm going to focus on how we can detect localization failures because I would like to develop a fail-safe function for localization. In this talk, I will talk about recent my research that achieves localization failure detection with the probabilistic modeling. Before going to the main talk, I would like to introduce myself. I'm Naoki Akai and I'm PhD in engineering. I got my PhD at 2016, and after getting my PhD, I started research at Nagoya University. I think you know the Tokyo and the Kyoto, and they locate at here, and Nagoya locates here. I think you don't know Nagoya, but Nagoya is one of the 5 biggest cities in Japan. I had studied about mobile robot navigation. When I was a PhD candidate, I was participating in the Tsukuba Challenge. So Tsukuba Challenge is a competition of the outdoor mobile robot navigation. In the challenge, we are doing autonomous navigation in the real city environments. In the real environment, many people make the occlusion for the robot sensor. And to achieve navigation in this environment, we need a robust localization. And when I was a PhD candidate, I was studying about the localization using a magnetic sensor. And my current research is advancing localization. I think this word is not general. The objective of this of my research is to realize things that general localization cannot do. For example, estimating reliability and detecting failures. I think straightforward localization research focuses on how we can improve localization accuracy and robustness. But in my opinion, even though we could improve localization accuracy and robustness, it is difficult to guarantee safety of the localization because guaranteeing safety and improving localization performance are different approaches. And I think so we need a new localization method and we need to extend the general localization framework. That's why I'm saying my research is advancing of localization. And also, I'm focusing on how to realize sophisticated diffusion of model and learning-based methods. Model and learning-based methods have advantages and disadvantages, and probably we can improve their performance if we can effectively fuse the model and learning-based methods. However, if we simply fuse them, so we cannot improve the performance, and so we need a sophisticated fusion. And I propose a hybrid localization and semantic localization. And we have a policy in these researches that we would like to enjoy explainability with a probabilistic modeling, even though we use a deep learning. For example, in a hybrid localization, we have a deep learning based localization. And in the semantic localization, we have a deep learning based semantic segmentation. Of course, it is not easy to enjoy explainability of the deep learning based methods. However, in these systems, the deep learning based methods are integrated to the probabilistic model for localization. And as a result, so we can enjoy the explainability of the localization system. In this talk, I'm focusing on these two topics. Okay, first I'd like to talk about how we can bring the reliability into localization. In this method, so deep learning is used to classify the localization failures. However, we do not directly use the deep learning to estimate the reliability. So we have some technique to handle the uncertainty of the deep learning. First, I'd like to explain a probabilistic model for general localization. In the probabilistic model, we have a robot pose, control input, sensor measurements, and map. And the robot pause is treated as a latent variable, and we would like to estimate the probability over the robot pause. The probability over the robot pause is calculated using this equation. If you see this term and this term, you can find this term can be decursively updated using these two terms. That's why this equation is called the Casper-Based Filter. In these equations, we have two important models called motion model and measurement models. If you want to improve the localization accuracy and the robustness, so basically you need to improve the measurement model. Here, I'd like you to ask what we can know from the probability. From the probability, we can know uncertainty of the estimate. As I mentioned, so in the probabilistic localization, we will compute the least probability. And because we have a probability over the robot pause, so we can have this kind of distribution. And this distribution represents uncertainty of the estimated pause. And from the uncertainty, we can also know about the confidence. For example, so here we have two examples. In the left example, so we can say this is unconfident estimate because the distribution is so large. On the other hand, in the right hand case, we can say this is a confident estimate because distribution is small. So as you can see, so from the probability, we can understand the confidence of the estimate. Here, I would like to consider about the difference of confidence and the reliability. So we also have two examples, and in these examples, so we have ground truth. Of course, ground truth cannot be available in the actual localization phase. However, we would like to introduce a ground truth to explain the good examples. In the left-hand case, we can say this result is reliable because the estimated pause and the ground truth is very close. However, so this result is unconfident because the distribution is so large. On the other hand, this result is confident because distribution is so small. However, the reliability is small because the ground truth and the estimated pause are far. From these examples, we can understand that the confidence and the reliability tell us the different things. This means that we cannot know about the reliability even though we solve the general localization problem. So we need to add a process to know the reliability. Here I would like to explain important related work, learning to detect misaligned point clouds, presented by the Professor Magnussen and the Professor Kuchner. They are organizers of this workshop. In this paper, they are discussing how misaligned point clouds can be detected. For example, in this figure, we have 2 point clouds depicted with the red and greens. And in this case, we can say these point clouds are well aligned because 2 point clouds are matched well. However, in this case, we can say these point clouds are misaligned because we can see some mismatches. If we can detect these kinds of mismatches, we can use this technique to detect the localization failures because the localization is doing the same thing. So in this paper, they used a lot of methods, including threshold and learning-based classifiers, and they compared many methods, and they showed that AdaBoost had a better performance to detect misaligned point clouds. In our reliability estimation methods, so we also use this kind of the misaligned point cloud detection method. However, we do not use it directly, so we integrate this classifier to the probabilistic modeling for localization. And as a result, so we can cope with the uncertainty of the misaligned classifiers, and we can enjoy the explainability of the classifiers. In our method, we use a convolutional neural network based classifier. And in order to develop this network, we refer the two-channel model presented in this paper. The network receives two gray images and calculates this similarity. In our implementation, we created two gray images. One of the scan image and another one is the map images. and we merged these images. If localization successfully works, we cannot see any mismatches in the images. However, if localization doesn't work, so we can see some mismatches. Our network receives these images and try to classify whether localization has failed or not. So this is a log curve to evaluate classification performance of this network. If this curve forms an exact square, we can say this network has a perfect classification performance. As you can see, this network has a very nice classification performance. However, there are some misclassification results. So we can say this network is quite accurate, but it's imperfect to classify the localization results. So, and also we can say this network has uncertainty in their outputs, and we need to handle the uncertainty. And to handle this uncertainty, we integrate this network into the graphical model of localization. Let me introduce how we can integrate the deep learning output into the localization model. So this is a general localization model that I explained before. The output of deep learning is introduced at here because deep learning receives robot pose, sense measurements, and map to classify whether localization has failed or not. So this is introduced at here. And also important thing is this is introduced as a gray variable. This means this is a conditional variable to estimate the robot pose. This means that we can use the deep learning output as a sense measurement. In other words, we can use it to estimate the target variable. In addition, we introduce the localization state as a target variable for the estimation. This state has two variables, success and failure states. Because we introduce this state at here, so we can use the output of deep learning to estimate this variable. And because we explicitly introduce the localization state, so we can know the reliability by calculating this probability. Because if ST equals success, this means the localization has succeeded. And because we can calculate this probability explicitly, we can know the reliability from our new model. Let me briefly detail the new models. So in our new model, we will try to the joint probability over the robot pose and localization state. In the general localization model, we will try to estimate the probability over the robot pose. However, in the new model, we will try to estimate the joint probability. In addition, the D, this is the output from the neural network, can be used as a conditional variable. This distribution can be decomposed, and the pose distribution is calculated using this equation. Let me compare the pose distributions by general and new ones. Top one is estimated from the general localization model, and the bottom one is estimated from the new localization model. And difference is here. In the general localization model, the likelihood is calculated using only this term. However, in the new proposal, we can use this term and this term to calculate the likelihood. In this term, we have a least distribution. This is a distribution over the CNN outputs, and we defer this output as a decision because CNN tries to decide whether localization has failed or not. That's why we defer it decision model. And by using this decision model, we can handle the uncertainty of the deep learning. Let me detail how the decision model works. As you can see in the decision model, the pose and localization state variables are given as a conditional variable. And based on these conditional variables, we can do the offline test. And based on the offline test, we can model trend of the deep learning outputs. And because this distribution models the trend of the CNN of the output, we can calculate the likelihood against the decision of the deep learning by using this model. In our new model,
likelihood for localizing the robot pose is calculated using the measurement and the decision models. As I explained before, this distribution models trend of the deep learning's outputs. It can decrease likelihood against suspicious decisions. Because our model can use this term to calculate likelihood for the localizations, so we can cope with the uncertainty of deep learning outputs.
So let me show you a reliability estimation example. So in this case, localization successfully works always. In other words, localization results are always reliable. In this video, the sensor measurements are depicted with red. This is measured by the 2D LiDAR, and the black points are mapped obstacles. That's why so we can say localization has succeeded if the red sensor measurements and black mapped objects are correctly matched. So in this case, so every time the sensor measurements and map are correctly matched. And this is a reliability estimated by our new system. Our system can estimate this is a reliable localization results. By using this reliability, we can explicitly know so this is a correct localization results. However, you might doubt that, so I'm just showing the reliability which is close to the 100%. Okay, I'll show you the next case where localization will fail due to incorrect motion parameters. According to the movement of the robots, we can see some mismatches between map and sensor measurements. And also you can see the blue arrows are expanded. So the new system is implemented using the particle filter, and this expansion with the blue arrows means particle distributions are resetted, and this reset will be performed if the reliability is less than 95%. That means if our system estimates this is an unreliable localization results, so estimate using the particle filter will be resetting. As you can see, if we can see some mismatches between the sensor measurement and the map, the particle filter will be going to reset. So this means these results show that the estimated reliability can exactly describe whether localization has failed or not. And so because by using this reliability, we can explicitly know whether localization successfully works or not. This is a quantitative result of the new localization system. The red one is the ground truth trajectory, and the blue one is the estimated trajectory. So in this experiment, we also use the incorrect motion parameters, and the tracking of the robot pose has been failed. And this red one is position error, and the blue one is orientation error. And this red one is estimated reliability. So according to the increasing and decreasing of the estimation errors, so reliability is smoothly changed. And this green one shows the output of deep learning. Obviously, this deep learning's output is very noisy, more than estimated reliability. From these results, so we can say so our system can handle the uncertainty of the deep learning. In addition, the estimated reliability can describe whether localization has failed or not.
By using our new system, we can know the reliability against the estimated pose. In addition, we can mitigate the noisy inference of the deep learning output. However, so even though we can mitigate the influence of the deep learning, so deep learning is not an explainable one. If possible, we would like to realize more explainable failure detection method. Then I would like to explain explainable failure detection method via the misalignment recognition. This method is presented in the robotics and automation letters. So first, I would like to talk about what is the difficulty to recognize a misalignment. As I explained before, in the general localization problems, the measurement model is used to calculate likelihoods. And this is a measurement model. And in the measurement model, we have a sensor measurement and robot pose and map.
To calculate the model, it can be decomposed using the independent measurement assumption. For example, in this case, so we have a point cloud and it is denoted as Z, and this distribution means a measurement model against the point cloud. And this model can be calculated by multiplying the measurement model for each point. This decomposition can be performed using the independent measurement assumption. Owing to the use of the independent assumption, we can have merit and demerit. For example, as a merit, we can calculate the measurement model. If we cannot use the independent assumption, it is impossible to calculate the model in real time. However, as the demerits, the relationships between measurements are lost because independent assumption means there are no relationships between each measurement. That's why we can assume there are independent, and we can decompose the measurement model. Owing to the demerit, the entire relationships cannot be considered in the measurement model. For example, we have a misaligned point cloud, and we humans can easily understand they are misaligned because we can see the point clouds from like this view, and this viewpoint enables to consider the entire relation of the point clouds. However, as I explained, now we cannot use this kind of view, so it is impossible to introduce viewpoint in the measurement model. To understand the importance of the entire relation, I think this is a good example. Now we have a mapped obstacles, and also we have one scan point. And I have a question to you. Is this scan point correctly aligned? I think this is a difficult question because we cannot decide from only one scan point. For example, if the scan points are like this, we can say these scan points are aligned to the mapped obstacles. However, in this case, we can say this is a misalignment. So as you can see, maybe you can understand considering entire relation is very important to decide the point cloud are aligned or not. However, as I mentioned before, in the measurement model, we cannot consider the entire relationships. So in order to detect the localization failures, we can use a threshold. We can set a threshold to the measurement model values, and probably we can detect failures. But in this case, this method just theoretically decides with a misaligned case, because we cannot consider the entire relation in the measurement model. To overcome this problem, we need a new model which enables to consider the entire relationships, and we propose a new graphical model that is a Markov random field with free connected latent variables. In this model, so now we have a sensor measurement and mapped objects, and from the relationships we can have a residual errors, and these residual errors are treated as observable variables. If we just have these observable variables, so we do not have any relationships. However, we set latent variables as a parent variable of these variables. In addition, we add the connection of between latent variables, and these variables are fully connected. Via the free connection, we can consider the entire relation of the measurements. and Z is a measurement class: aligned, misaligned, unknown. So in this model, we are trying to estimate the posterior distribution over the Z, and by estimating this probability, we can recognize whether the measurement classes are aligned or misaligned.
So this is an example of the misalignment recognition. If the sensor measurements are depicted with red, this means the measurements are aligned with the map. And if blue, this means the measurements are misaligned. So in the case where the misalignment occurs, so we can see some mismatches between the measurement and the maps. However, sometimes we cannot see any mismatches, for example here. However, our method can understand this is a misalignment because our method enables to consider the entire relation, and if we have a misalignment here, this should be the misalignment. By using the full connection, we can consider the entire relation of the measurement, and we achieve the exact misalignment recognition. We created a dataset that has the success and failure localization samples, and we conducted a classification performance of the localization results, and we compare the proposed method with the convolutional neural network one that is explained before one. And of course, CNN-based method had a better performance. However, our method can outperform the CNN. In addition, the most important thing is the proposed method is a very explainable one because this is based on the probabilistic modeling. So this is a summary of my talk. I'm sorry I cannot attend this workshop. I'm very glad so if my talk could be some help to make new research ideas. Thank you for watching. If you have any questions, please feel free to contact me.